So today we're going to be looking at an adiabatic flame and determining the temperature of the flame given inputs of natural gas and just regular atmospheric air. So we're going to have our flame be like a little Bunsen burner. Let me make this bigger. So we have our burner, and then we're going to have inlets of natural gas and then also air. Now we're going to have a flame coming out the top. Terrible flame. Let's try that again. If I label it, it's alright. So our air coming in is going to be comprised of oxygen and nitrogen. We're going to ignore the other elements that are in there like argon, but we're just going to go with O2 and N2 for now. And we know that these generally in the atmosphere come in a 21 to 79 ratio. More realistically, it'd be something like 21 to 78 with the remaining 1% being argon, but for now we're just going to leave it as this. And then our natural gas is going to be comprised of some methane, some ethane, and some propane. And so our goal is to determine the temperature of the flame when we combust these together. And the way we're going to go about doing this is determining the ratio of moles in our inlet and our outlet streams, and then using some equations for the enthalpy of the reaction and to determine the change in enthalpy throughout the reaction. So first off, let's start off with the stoichiometry of the combustion of each of these. So we're going to have CH4, and that'll have some coefficient that we'll get to, plus O2 combusts, and it forms CO2 plus H2O. Running out of space here. Let me move everything to the side. So for CH4, it's going to be the same thing. We'll have CH4 plus some O2 yields our CO2 and some H2O. And then this nitrogen isn't going to be part of the combustion, but it's going to be along for the ride, and we're going to need to include it because as the flame is produced, the nitrogen is going to have to be heated as well, so we're going to need to include it in our equations. So we'll have some N2 along for the ride. So right off the bat, we see that only one product on our right-hand side has any carbon, and only one product has any nitrogen, or not nitrogen, hydrogen. So we need to match those up. So we have one carbon on the left-hand side and 4 hydrogen on the right or left-hand side. So the carbon's already matched. We need to match the hydrogen. And then we need to match the O2. So we have 2 O2 here, and then we'll have 2 more O2. We'll have 2 more oxygen here. So in total on the right-hand side, we have 4 oxygen. So that will be 2 O2s on the left. So just to double check, 4 hydrogen, 1 carbon, and 4 oxygen, and 4 oxygen. And then our nitrogen comes in a 79 to 21 ratio to our oxygen. And since we have 2 moles of O2 coming in, we're going to need to multiply our nitrogen by the amount of moles coming in to make the ratio work. Then we can do the same thing for our ethane. We'll have C2H6 plus some O2 yields some CO2 plus some H2O plus some nitrogen. So we'll do the same thing. We need 2 CO2. Looks like we'll need 3 H2O. We're going to have 7 oxygen total. So we'll have 7 over 2 O2, and that will yield 7 oxygen. And then for nitrogen, we're going to have to do the same thing we did up here. We'll have 7 over 2 moles of oxygen and a 79 to 21 ratio. And we can do that with propane finally. And by the way, I believe the percentages of these are going to be 95%, 4%, and 1% in our inlet of natural gas. So we'll have some propane, C3H8, plus some oxygen will yield some CO2, some H2O, and some nitrogen. So we just got to balance things again. We have 3 carbons, we have 8 hydrogens, and then total we have 6, 10. We'll have 5 5 O2s. So we'll have 5 times 79 over 21 N2. Keep forgetting the N2. So double check that. 3 carbons, 8 hydrogens, 10 oxygens. Yep. And then the nitrogen along for the ride. So something else that we're going to be including in this scenario is an 20% excess of air. So the important thing to note here is that when we're including an excess of air, it's going to decrease the temperature of the flame because we're going to have some O2 and some N2 that's going to be going through the system and will need to be heated as well. But it's not going to take part in the reaction and producing heat because we're already going to be combusting all of our natural gas. We'll just have excess O2 and N2 that we'll need to include in the enthalpy in the enthalpy equations. And that'll just be 20% of the amount that we put in because we're assuming that baseline it's perfectly balanced. When we add the extra air, since it was previously perfectly balanced, all the extra air that we're putting in just needs to be heated up, but it won't be taking part in the reaction. And then one more important note about this scenario is that we are going to be considering this as an adiabatic flame, just meaning that no heat is going to be lost outside of the system. So we're going to assume the walls of the burner are perfectly insulated. And we're also going to be assuming this is in steady state. So the amount coming in, the amount of air and natural gas coming in is going to be constant throughout. So I'll just make some notes of that here. Adiabatic, so there will be no heat loss. So we won't need to consider our surroundings. And then we won't need to consider any changes over time in the amount of natural gas and air that we're putting into the system. And then that will also mean that the derivatives of the energy or the heat of the flame are all going to be 0 because there's no change in the energy between the inlet and the outlet. There's no change in the difference in energy between the inlet and outlet.